Hello everyone, I have some really cool content for you today about stepper motors. Over the last 6 months to a year, we've had so many different people looking to maximize the speed and acceleration of the 3D printer. Granted, there's a lot of other limits related to extrusion and things like that, but it is a really interesting optimization problem from a stepper motor kind of motion perspective. And so, as we've been looking at, accelerations from 5,000 millimeters a second squared pre-input shaper to 10,000, and we've even had people running up to say 80,000 plus. It turns out we have a lot more overhead in kind of torque capability than we initially thought. The key is to be able to pick the correct motor and parameters in order to hit those values that you're interested in. This doesn't answer the question, should you do those, but it lets you know, can you? And so this model, again, has been developed with a lot of input from friends who are more knowledgeable than I am, but it is a good kind of first pass theoretical estimation of how your stepper motors will perform in your XY motion of your 3D printer. So when you're looking for a motor, the first thing you want to do is be able to find a spec sheet for something that you're interested in. In this case, this stepper motor is the default stepper motor for the Voron Trident and the V2. I believe a few other printers use it as well. But you'll note there's a few things. First of all, it is a NEMA 17 motor, which defines the kind of size. And then it's a 48 millimeter deep motor. That isn't particularly important for our calculations, but it's just good to know in general. How that comes into play later on is it defines or helps change our rotor inertia, which is essentially how hard it is to accelerate the rotor of the motor itself. And as you drive larger and larger accelerations, that rotor inertia hurts you, because instead of driving the tool head, you also have to drive the tool head to a certain speed, as well as the rotor inertia to a certain speed. The parameters we're particularly interested in, though, really are these other parameters. Amps for phase is the current going through each of the windings. Stepper motors, in this case, have two separate windings that turn on and off in order to rotate the rotor. And in this case, it's rated for 2 amps of current. We have resistance, essentially, as you apply voltage to one side of the winding and allow current to flow through it, it has a certain resistance to that current. Inductance is the measure of basically how difficult it is to turn on the coil and then turn it off. An inductor tries to maintain current at a steady state, and that's really not important in the case of, say a heater or something like that, because you're going to keep that heater on at full power most of the time. However, with the stepper motor, as we are moving the tool head around, that stepper motor is energizing and de-energizing those windings, and that happens really fast. So every time we need to switch from one winding to be energized to the other, that means that one winding has to stop current flowing through and the other winding has to start current flowing through. And since inductance is a value that resists that change, it's a really important parameter for us as we're looking forward to faster and faster speeds. And you'll see this more in just a minute. The next thing is holding torque. So this defined our peak value and kind of the flat value of the torque curve, which we'll see in a moment. And this is important in general, but a lot of the times until you get to super high accelerations, it's not actually the limiting factor. Step angle, again, there's 1.8 degree steppers and 0.9 degree steppers that are common in 3D printing. 1.8 degree steppers will always be best from a pure speed standpoint, because you don't have to step as many times per rotation. With a 0.9 degree stepper, the windings have to be energized and de-energized twice as fast, and so that inductance, that resistance to change, becomes a bigger factor, and you'll see those in charts in the future. We've already talked about rotor inertia, so we'll skip over that one. And then the rest of this is really related to temperature and things like that, which generally in our case with lower ambient conditions, and we're running these at lower current than the maximum kind of defined, value, we're not running into any issues here. Now that we've taken a look at the spec sheet, let's go ahead and check out this graph here, which is essentially the same representative shape of any stepper motor you're going to look at. There's always going to be two areas of the curve. The first one, up to a certain speed, is current limited. What this means is that essentially the stepper motor and your stepper driver and control board can supply the maximum amount of current that the motor can handle. In this case, for this motor, it's 2 amps, and so we get the full rated torque up until this point. At this point, though, due to the inductance and the back EMF voltage, which we'll talk more about in a second, the system cannot generate enough current for the motor. And so since the current starts dropping off as we go up higher and higher speeds, essentially the available torque also drops off. And so this is why most of the time our loads and our speeds are more in this range of this chart. And so, we don't need the full amount of torque, but what we end up seeing is a layer shift once we reach this point where our system torque is higher than the torque that the stepper motor can provide. So here is essentially the math behind everything we're looking at. And this was provided to me by David on Voron Design, and it's been really helpful for me moving forward. But let me just talk about it for a second. So in this case, we have a specific motor that we've been talking about. We have a revolutions per second, which gets converted to millimeters per second in my calculator. And then we have a few parameters. What we essentially care about, though, is this V generated, and that is the back EMF voltage that is generated by the motor as it is spinning. So that again is why your LCD display may come on and you may blow out a control board if you start moving around your tool head too fast while the unit's powered off. So as you go faster and faster, the stepper motors are generating a back EMF voltage that is higher and higher. The thing though is that you only have a certain amount of voltage available to drive your motor. In this case, we are specifying that input voltage as 24 volts. And so to calculate how much voltage you actually have available to generate current, we subtract our 24 volts from our generated voltage and get the available voltage. As you can see, as we get faster and faster, this voltage continues to drop, which is essentially what causes our reduced performance at higher speeds. Our I available, theoretically, is the amount of current that we could actually push through the motor. Again, this is significantly higher than the motor would handle, and you're probably going to burn up your motor if you ever set up a value like this. So that is why in firmware we limit our max current to something much lower than even the 2 amps that our motor is rated at. But in this condition, you can see here up until a certain point, this is that flat area of the curve where our supplied current matches the rated current of the stepper driver or stepper motor. Once we get here, though, your voltage that is available once you subtract 24 volts minus your generated voltage, this voltage is too small to drive the maximum amount of current. And that is because if you look at voltage equals current times resistance, we know the voltage here that is available to generate current, and we know our phase resistance, so then we know the maximum current that we can supply. So this is a fraction of the max current and then the max torque. So then we essentially scale our maximum torque by the current that we're actually supplying. There's two different things here. There's the maximum torque when 2 coils are energized versus 1 coil energized. And since we're microstepping and a bunch of other math behind the scenes with the stepper drivers, my understanding is we're never getting the full amount of torque here that we would otherwise. So to be conservative, I've used the single coil torque values in all my charts moving forward. So we are almost to the fun stuff. So essentially I have a database of a bunch of different stepper motors that I can easily pull from and plot and compare them all together. And then I have all of the input parameters tied together so that it adjusts the parameters for all of the different motors at the same time. Input voltage is really critical. As in the last slide, you could see that the amount of current we can push essentially is limited by our input voltage, which is why a lot of people are looking at 48 volts. Max drive current, in this case, I have it at 2.5 amps, but know that if you're using 5160s, 2.5 amps might be possible, but for say a 2209, that's above its practical threshold. And then if you're looking at scaling that down by a certain percentage, a lot of times we don't run our stepper motors at the maximum kind of current that it is rated for. The next thing is this pulley size. So in the previous slide again, we were talking about revolutions per second. We need to convert that into millimeters per second. And so I have a variable pulley size that I can adjust. If we want to do, say, 16 teeth, your curves are going to change versus 25 teeth, etc. You can just see how everything behaves. Gear ratio is for, say, the V2.4Z drives. We're not worried about that today. Then the final values here are essentially we need to figure out where our torque availability from our stepper motor matches our torque needs from our printer. And so I've done a really simple estimation here where we're just looking at force equals mass times acceleration. So in this case, I have 500 grams for the tool head and moving mass. And then say if we put 10,000 millimeters per second squared, we get a nice red dashed line that's straight across the entire range that says we need to at least be this much torque. If we are below this torque, below the red line, all of these regions would be areas where the stepper motor does not have enough oomph to reach those values, and so it would layer shift. So there's a lot of assumptions here. We're not looking at any extra restrictions. Say if you put too much grease in your linear rails or anything like that, those damping characteristics would be a function of speed, and they would increase as you go faster and faster. But for a good first pass, we're just looking at a flat straight line. So now that we have this, we can tell that this motor at 24 volts reaches up to around 600 millimeters per second, give or take a bit. And we have been using this motor for a long time because before kind of the industry switched to 24 volts, we were all running 12 volts. And if you drop the 12 volts, you'll note that that drop off happens really fast now. Because again, that back EMF voltage is ramping up really quickly. We don't have a lot of extra voltage available, so our current that we can actually drive drops off substantially. Since the V2 and the V1 and things like that, most of the time were around 300 millimeter second travels. Again, this was about the only motor at the time that was readily available that could hit that 300 millimeters per second. So that lines up really nicely. At 24 volts, though, we have a lot of overhead. Most people aren't using 600 millimeters per second travels, so there's a lot more motors that can work in our instance. There's one or two more things I want to mention here, just because otherwise it might cause some confusion. When you remove this acceleration, you'll notice that this blue line with the available torque shifts as well. And the reason it does that is because this torque is essentially a calculated available torque. So I am subtracting the amount of torque that is required to accelerate just the stepper motor's rotor inertia from the torque value. So the stepper motor can produce this much, but a certain amount gets subtracted because it needs to accelerate itself, and that torque available to accelerate the tool head gets reduced. So if we go all the way to 100,000, you'll see that pretty substantially because this drops off substantially. Also, you'll note that this dashed red line here also increases as you're increasing the acceleration. So in this case, there's a certain point, say around 90,000 acceleration, I think, where you can reach this value, but you're right on the edge, essentially. And I believe Josh Murrah has gotten around these values. And of course, that's insane. I'm just being honest. Being able to accelerate a tool head at 90,000 millimeters per second squared is just, you're going to vibrate a lot of stuff. And It's almost like a top fuel dragster where you have to repair your printer more often. But I just wanted to go over that to make sure that you understood why the lines were jumping around. The other thing is with pulley size, you'll note that as I change this value, not only will the blue line change because essentially it has to run faster to go the same amount of speed, but also the torque required changes because now the ratio of revolutions per second to kind of millimeters per second has changed. So torque changes as well. You have an advantage of torque because your moment arm is shorter with a 16-tooth pulley, but your back EMF is higher because you're going faster or you're rotating the motor faster for the same amount of linear speed. And so that's why you'll see that actually a smaller pulley size, even though you have a torque advantage, let's jump back and forth here a bit. You'll see that the required red line torque drops, but the stepper motor torque drops faster. So you actually get a net loss in speed. So that's why Jared on Voron Discord has been experimenting with 25-tooth pulleys, mainly with 0.9 degree steppers, but it gets you a little bit more top-end speed if you're going for that. Now let's bring in a second stepper motor. And this is the 17HM19 2004S. Has almost the same part number as the previous motor, except it is a 0.9 degree stepper instead of a 1.8 degree stepper. I really like this motor. I have it in 2 of my printers, mainly because of noise. You'll see though that the max torque at the lower speeds is reduced, as well as the fall off is quicker because again, the 0.9 degree stepper means that the coils have to turn on and off twice as fast, and so that back EMF voltage will be twice as high. In the end, you'll see that the maximum speed gets dropped fairly significantly. So, again, if you're printing in the typical 0 to 300 millimeters per second range, you'll be fine with either option. But if you're really pushing the limits, it may not be enough. If we jump back to 12 volts, though, and we look at, would it have been okay to run a 0.9 degree stepper at the lower voltages, you'll see that in these conditions, granted we're at 20,000 acceleration now, but you really would have had to cap your acceleration and speed down substantially without getting layer skipping. So you just have to understand what your goals are, but the other option is to always increase voltage past 24 volts, which is what we've been seeing some people do. I've done, Josh Murrah has done, a few other people have as well. But if you increase to 48 volts, essentially the whole world changes because, and I'll scale this back to 2,000 millimeters per second because we're really out in that range now. Essentially, again, because you have the additional overhead voltage, your transition from current limited to voltage limited is extended out substantially higher. So you can hit a lot higher speeds. Again, you need special drivers. There's Rotor 5160s specifically that support 50 volts. And then you typically need a control board that can also support 50 volts because the capacitors under your stepper drivers typically are only rated for 35 volts. So there's some hacking to do. There may be some products in the future though that allow this to be done easier. Maybe it's great for a pick and place machine or something like that you need maybe faster travel speeds. There's a lot of advantages here, even though it is higher noise and wear on your machine and things like that. So finally, as I wrap up to this video, I'll plot a few more motors here, including the 2 motors that come kind of spec with the LDO kit. Let's see here. The gray motor here is the kind of Z motor that they used. And then the other one, this 40 millimeter 2 amp MAH motor here is an alternative for the A and B drives. So again, it's a shorter motor at 40 millimeters instead of 48 millimeters. So the rotor inertia is a little bit lower, but it still has plenty of torque. The last motor I want to talk about is this LDO 42 STH47-2504AC. And this is used, I believe, on some of the rat rig models, and it's just becoming available in the US. But If you are looking for maximum speed and acceleration, there's really no motor that really comes close that I have seen. It is some of the lowest inductance motor I've ever seen, as well as fairly high torque. It is a 2.5 amp motor though, so to use it to its fullest potential, you'll definitely want those 5160s. As a thought experiment though, let's bump this up to like 80,000 millimeters per second squared. It has to calculate everything here. Just 1 second. That's still looking good. And then if we go say 90,000, still calculating. Just thinking about it. There we go. So 90,000 might be slightly too much for that motor, but theoretically, you could almost hit, say, 750, 760 millimeters per second at, say, 85,000 millimeters per second squared acceleration, which would absolutely be bonkers. I'm sure it would be super loud too. But if you wanted to try that out, this is really the motor to pick up. There are the 60 millimeter motors and other options like that. Let me pull up one of these here quick. Just a second. Like this one. Has super high torque, but it falls off fairly quickly. So you could hit higher accelerations, but you would not be able to hit those accelerations at fast enough speeds. So there's always a trade-off between, again, that higher torque at the low speeds versus, the adequate torque at these speeds you're trying to hit. So I'm going to upload this Excel document. It does have macros in it because it calculates all this stuff in the background. I will upload it to my GitHub page and I'll link it in the description so you can play around with the different parameters. Again, this is based on David's work from the Voron Discord. It was great to help me with that. So play around with it. If you feel like adding extra values, feel free to reach out, send me data sheets. I tried to keep this database up to date with links to different motor pages so that if you're looking for it in the future, you can always reference the value. Or, assuming if I entered it incorrectly, it can always get updated. So, without anything else, that's basically the extent of this discussion today. I really wanted to kind of step you through this and give you some information so you can play around with it, because I think it's a fun thing to experiment with and just double check to make sure that the motors that you are using or purchasing don't show up as duds and they actually end up doing what you're looking to do. Or if you're a vendor or a kit supplier, making sure that your specs are adequate. So today again we've discussed the primarily XY constrained acceleration and speeds. I will talk hopefully in the future about extruders, and extruders are a little bit different because they're not really speed constrained. You're always in this kind of flat current limited constraint, but a lot of the times you're actually kind of heat limited because they're so small, and with the higher winding resistances, the power generation is fairly high. So you have to reduce the current to not melt your ABS parts or things like that. So we actually have to look at that from a power dissipation standpoint and power limited standpoint rather than a, say, max speed limited standpoint. That's really cool. So if that is all for today, feel free to add questions or comments and I'll try to answer them as best I can. Hope you enjoyed it. Thanks.